This is an example for our previous class. So in our previous class, we studied about basic identities of Boolean algebra. So actually, I summarized all the equations here. So we're gonna use this one in order to solve these given questions. Okay. So actually, these questions are very widely known, well-known examples for these kinds of Boolean algebra. So I hope you guys be very familiar with these equations and questions. So because sometimes you may have some complicated questions, but if you are very familiar with these ones, then you might be able to solve the problems easily and quickly. So that's why you need a lot of practices. Okay. So let's go with the first one. Okay. So here, you have x and xy. So then you can think that you have that one. So then you can use this one. Okay. When you have a variable, and then you have one, and you have AND operation inside, then you can get this variable again. Okay. That's why you can say that this is x dot one. So this becomes x1 plus xy, and then you can combine these two terms with x. Okay, then you're gonna have x and 1 plus y. Okay, so by using this one, number 3, and then this again becomes 1, then eventually this becomes x. Okay, that's why you have to keep in mind this result. So actually you can use set theory in order to solve this one. Okay, so I told you that you have 1 here, you have that here, you have 1 here, and you have that here. So this is x, and 1 means entire sample space. This is 1, and that means AND gate, which means intersection in set theory. That's why you have to calculate the intersection with the entire set and x. That's why x itself becomes the intersection. That's why this is x. So then this one, you have to calculate the intersection between x and y. Okay, because you have that inside here. So then you have union, okay, eventually, because OR gate means union in set theory. That's why you have x, you have union with this one. That's why again you have x. So you can get this result easily. So you can think about the set theory in order to solve these kinds of Boolean algebra. So you have another example here. So let's use the basic identity of Boolean algebra in order to solve this one. So then, as you can see here, you have x and x in the left-hand side and right-hand side both. That's why you can combine the two terms with x. That's why you have x and you have y plus y prime. Okay. So then you can see that here. Here you can see that you have this one, x plus x complement equals 1. That's why this becomes 1. So this becomes x dot 1 becomes x, as we did in previous example. Okay, so you can also use set theory for this problem. So here you have y here. This is the complement of y. That's why the others, and then you have union. It means that this is entire set. Okay, so you have x and number 1. So as I told you before, 1 is the entire set, and you have x inside there, and then you can get the intersection. That's why you can get this one, x itself again. That's why you can use set theory in order to solve this question too. For the next one, you have another example with this one. So then you can use number 15. Okay, so you can use number 15. So we did this one in our previous example in page here, page 10. So if you want to review this problem, then you can go to page 10. Okay, then we did the same thing. So here this can be A, this can be B, this can be C. So then as we did here in number 15, identity rules, and then you can say that this is x plus x prime, this is x plus y. because this is A, B, A, C. So eventually, this means that this means 1. So as we did here, number 7, and then you have x plus y. And then by number 2, this becomes x plus y, and that's it, okay? So actually, you can use set theory for this one as well. So here, so here, you have x, you have y, and this is x itself. That's why you have this one. This is x complementary. That's why you complement. That's why you will gonna see the others except a x, and then you have to get the union intersection with y. That's why you have to get this one, okay? And then you are getting the union of them. That's why this is the entire result. This is the final result. This equals to xy, x union y, x plus y, okay? So then you can see that they are same to each other. So next example is this one. In this example, you can easily see that you can use the distribution law. Okay, you can use the distribution law. That's why this becomes x plus xy, and then as we did in number 6, this becomes x only. So x plus xy, and then you have that one here. That's why you can combine with x just like that. And then, but anyway, this is same with this one, number 1. That's why you can easily see that this is exactly same with x, and that's it. You're done. Now you can use set theory for this one as well. So here, you are doing the x, y union, okay? And then you have x, and then you are getting the intersection. That's why this is the intersection, right? That's why the result should be x. That's it. So number 5, in number 5, you are using the law which we used in the question 3. So question 3, we use the law just like that. Becomes a plus b, a plus c. So this is a, b, a, c. That's why you can say that this is a plus bc. That's why this becomes x plus y, y dot, right? So then this is 0 by this one, number 8, okay? That's why this becomes x plus 0. That's why this is x. So you can use set theory here as well. So here you are doing the union and x and y. And you are doing the union x plus y complement. That's why it becomes this one, okay? And then you want to find the intersection. So this is x plus y. This is x plus y complementary. That's why you x plus x and y complementary. So you have these ones, right? These ones are this one, okay? So you can finally get the x from here. So in this case, you can use the distribution law. That's why this becomes xx prime plus xy. So this is 0 by this one, number 8. That's why you only have xy, and that's it, okay? So you can use this kinds of rule. You can solve the given problems using these basic identities of Boolean algebra. It's very easy and straightforward. However, during the quiz or exams, you may have a lot of questions. That's why you might be in trouble. That's why in order to handle that kinds of unexpected situations, you need to get a lot of exercise. Or maybe you wanna memorize several questions if you want. Okay, then you can solve the problems very quickly. So here in next slide, I would like to give you some solutions for our previous examples. That's why if you want to review the contents in this lecture slide, you can use this slide, okay? And then now we are looking at the consensus theorem, okay? So here you have x and x prime, okay? Then you have x and x prime. Now you have y and g. So then, if y is here, g is here, then this can be ignored. This is called consensus theorem, okay? So we have to prove this one, right? So in order to prove this one, we can develop this one, and then we have to see this goes to this one finally. Okay, so let's start with the first one. Okay, this is our given equation, and then for the first two, you have the first two, so this becomes yg dot 1. Okay, this is by number 2. Okay, and then by number 7, the 1 can be x plus x prime, right? That's why this becomes this one. Okay, and then you can develop, okay, by distribution law, and then this is distribution law, and then you can do the ordering in terms of the alphabetic order. You can make a sorting in terms of alphabetic order. That's why x becomes the first, x prime becomes the first, and then you have to put yg and yg, and then this is same with the previous line. And for the next you have to combine with x, and then you have to combine with x prime. Okay, when you look at the x, and then you can see that is also with y, so that's why you have xy, and then here you have 1, and here you have 1, that's why you have 1 here, and then you have g here. In the right hand side you have g here, that's why here you have xg, x prime g, that's why you have x prime g, and 1 is here, y is here, right? That's why you have this result and this result. And now by this one, number 3, or when you have something and plus 1, it becomes 1. That's why this becomes 1, this becomes 1. So when you are doing the multiplication with 1, AND gate with 1, then it disappear. That's why you only have xy, you only have x prime g, and that's it. You prove this one, okay? So this is the application of this consensus theorem, okay? So in this case, you have to develop this one: a prime, ac, b a prime, but you can make a sorting in terms of alphabetical order. That's why you have a prime and b, and then you have bc, right? And this becomes 0 by number 8 rule, right? That's why by number 8 rule, this becomes 0. So you have this one, okay? And then you can check that. You have a and a prime, and then you have c and b, and then you can check that b is here, c is here. Then you can say that this can disappear. So you only have this one finally. So this is the application of consensus theorem. So by doing this one, you can reduce the number of the gate. So it's kind of a simplification procedure, okay? So now, up to now, we studied about the De Morgan's theorem. So by using the De Morgan theorem, you can make a complement of the function. So when you have function just like that, it has something. So for example, this is also function a plus b. You have the multiplication with d, for example. So you want to get the complement. So you make this one, or you are doing this one. They are same to each other. So you have this one, and then in entire function, you have a complement. So in De Morgan's theorem, in number 1, when you have a plus b and complementary, then it becomes a complementary multiplication, b complement. And number 2, you have a dot b, and this becomes a bar plus b, okay? So this is kind of De Morgan's rule, De Morgan's theorem. By using theorem, when you have any kinds of function here, and then when you have the complement on top of it, then for the first phase, you have to go to the De Morgan's theorem for sure, and then you are gonna do the development based on that. That's why you have to keep in mind that in order to calculate the complement of the function, and then you have to use the De Morgan's theorem, okay? So here, let's say that this is a, this is b, okay? And then this is function f. Function f is a plus b, okay? Now, you want to put the complement. So you have complement here, and this becomes a bar dot b dot just like that. So now you have bar x bar y g bar dot bar x bar y bar g, right? And then you can use De Morgan's rule here again, and then this becomes x plus y bar plus g, as you can see in number 2 of the De Morgan's rule. And then multiplication, this becomes x plus y plus g bar, and that's it. Okay, so this is by this second rule of the Morgan theorem. So let's go for the little bit more complicated one. So in F2, this is x, this is a, this is b. Okay, so F2 is x a plus b bar. F2 bar is just like that. So now you can imagine that this is another variable, capital C. Okay, this is capital C. So now it is same with x bar c, right? Then you can do this one, right? So then you have to calculate the c bar. Then c is a plus b, that's why you have to calculate a plus b bar. So now you have x bar plus a bar dot b bar, right? So then here x bar plus, let's look at what's the a. This is the a, right? That's why you have bar and y g dot bar y g. Okay, so this is x bar plus. So in this case we have to use the De Morgan's second rule. That's why this is y bar bar plus g bar bar dot y bar plus g bar, right? So when you have a complement of a complement, then that is y itself. This is g itself. This is y bar plus this is g bar. That's why you can get this result. Okay? So this is how you calculate the complement of the function. So when you want to calculate the complement of the function, then it means that you have to use the De Morgan's rule at first, because you have a lot of complicated rule at first, and then entirely you will get complement operator, and then for the first time you have to consider the De Morgan's theorem in order to escape that situation. That's why that is required. Okay, so in this case this is a, this is b. So now you can see that this is a plus b. You want to calculate the f1. This is f1, f1's complement. So then you want to get a plus b bar, then a bar dot b bar, and then you have x bar y g bar dot x bar y bar g. Okay, then you have to use the De Morgan's rule. That's why you have x plus y bar plus g dot x plus y plus g bar. Okay, this is what we can do for the first question. Okay, then let's go to the F2. So F2 is look like this one. So then we can say that this is x a plus b, for example. This is a, this is b. And then you have complement in order to calculate the complement of F2. So then you have x bar plus a plus b bar. Okay, and then x bar plus a bar dot b bar. Okay, and then you have x bar plus a is this one, right? That's why you have y bar g bar and bar dot b is y g, and then you have bar here. So x plus this becomes bar bar y plus bar bar g dot bar y plus bar g, and then this is x plus y plus g, because the complement of complement is itself. That's why this is y plus g, and then you have y bar plus g bar, and that's it. The same with this one. Okay, so it's very easy. So you have to be very familiar with this operator, because it's very easy and straightforward. But you are not familiar with this kinds of a calculation procedure, then you may have some mistake during quiz or exams. That's why you should be well prepared for these kinds of calculation. Okay, now we have to go for the standard form, which we have to cover until the end of this class. So in standard form, we have two definitions. The first one is min term, the next one is max term. Okay, min term is for the production rule, product term, and then So actually product is related to AND gate operator, okay? And then it is also related to intersection in set theory. So then in max term, it has opposite meaning. That's why you can easily imagine that max term may be related to sum term, right? Because you have multiplication for AND gate, summation operation for OR gate. That's why in max term, you may have some definitions about sum term, right? That's why you can see that it has sum term, okay? And then it has OR operation, as you can see. And then you have dot operation, as you can see. So here, and then in product term, every single result should be 1. In this one should be 1, in this one should be 1, and this one should be 1. That's why when you are doing the AND gate operator, the result can be 1, okay? The result can be 0, the result can be 1, but in AND operator, the unique solution is 1 when every single variable has number 1, okay? That's why you want to get this unique solution, okay? That's why when you have 0, you have to make complement. That's why you have bar here. When you have 0, you have another, you need to get another complement for y. That's why you have bar here. Lastly, in G, you have 0. That's why you need another complement. That's why you have G bar. That's why you have X bar, Y bar, and G bar in the first term. And then this is called M sub 0. So you have from M sub 0 until M sub 7. Okay, this is order of the all kinds of combinations with X, Y, and G, where X and Y and G are all 0 and 1. Okay, so let's look at the next one. So in this case, only these ones are 0. That's why we need to do the complement for these two variables. That's why we have complement for these two variables. In this case, X and G are 0. That's why we need complements for X and G. So X and G, we have complement. And then in the next, our X needs complement because it is 0. That's why only X has complement. For the next case, Y and G are 0s. That's why we need complement for Y and G. That's why we have complement for Y and G. For the next, we have 0 only in Y. That's why we need complement of Y. That's why we need this one. For the next, we need complement for G. That's why we have this one. That's why we have this one. Lastly, every single values are 1. That's why we don't need complement in this case. That's why we only have X, Y, and G in the last case. So in this case, when you put 0 and 0 and 0 and 0 in this case, your M sub 0 becomes 1. Obviously. For the next case, when you put this one, so M1, when you put this result, and then this becomes 0. Only this one has 1, right? So this is a unique solution in this table. So as you can see that these are all 1 and the others are all 0 in this min-term operator. Not operator, min-term calculation result, okay? Then now it's time to look at the next one, okay? For the next one, you have another definition called sum term, okay? So in this case, we are dealing with OR operator. We are dealing with OR operator. So in OR operator, you should be you should be able to get the unique solutions, okay? You should be able to get the unique solutions. So in OR, if one of the digit, if at least only when everything is 0, then you will get 0. Otherwise, all the other cases, they will be number 1. Because when you have at least one value, then you will get number 1, okay, in OR operator. That's why this one is our unique solution guarantees. That's why we have to make every single value to be 0. That's why this is okay, this is okay, this is okay. That's why we don't have complement in this case because we are doing the OR operator. Okay. So this is max term. That's why we have capital M. So we are from capital M sub 0 up to capital M sub 7. Okay. And then for the next case, G is 1. That's why we have to make this one 0. That's why we need complement. So we have complement. Here, y is 1. That's why we need complement of y. Next, y and g are 1s. That's why we need complements for these two, y and g. That's why this one and this one. And then for the next one, x is 1. That's why we need complement for x. That's why we have this one. For next, y and g are 1. That's why we need complement for x and g are 1. That's why we need complement for x and g. So we need complement for x and g. For the next, x and y are 1s. That's why we need complements for x and y. That's why we have this one. That's why we have complements for x and y. Lastly, every single digits are all 1s. That's why we need complements for all variables. That's why we need these ones. Okay. And then, as I told you before, we need a unique solution. Here, our unique solution is 0. That's why every single position, everything is 0, and the others are all 1s. Okay? This is our max term table. So, then it's time to see the relationship between the max term and min term. Okay, so here when you look at this one might be M3, right? So in M3 we have x plus y complement g complement. So y complement and g complement. This is M3, and then by De Morgan's theorem, this can be in De Morgan's theorem a plus b becomes a b, right? And then and also when we have a plus b plus c, and it becomes a dot b dot c dot. Okay, so then a is x, b was y prime, c was c prime, right? That's why when we have bar here, and this becomes x bar y g, right? So this is x bar y and g, and then we have complement here. So then you can see that this same is the small m sub 3, and then we have complement again. So we can see that m sub 3, capital M sub 3 equals to small m3 complement. That's why we can easily see that they have a complement relationship. Okay, and then by adding or substituting these min term or max terms, we can define entire logic circuit. So here we are adding up several min terms in order to make one function. So we are adding 1, 2, 3, 4 min terms, and the numbers are, this one is m sub 0, the second one is m sub 2, third one is m sub 5, last one is m sub 7, and then they are combined with a plus operator. That's why we can get this result. And then by our agreement, we can write down this one just like that. We are doing the summation. We are doing the summation of m values where the indexes are 0, 2, 5, and 7. That's why our indexes are 0, 2, 5, 7. Okay. And then we know that our f function is the summation of small m, where the indices are 0, 2, 5, 7. And then now you want to calculate the complement. That's why we can use De Morgan's rules again. That is possible. One thing we can try is that we can use this table. So we have entire set, and now our function f is for 0, 2, 5, 7. Then our complement will be the others. That's why m sub 1, m sub 3, m sub 4, and m sub 6. That's why these are our complement. That's why our complement can be denoted by the summation of small m, where the indices are 1, 3, 4, 6. Very easy. Okay. And then when we have the summation of small min terms, and then when we have complement, by the De Morgan's theorem, we can convert this one to this one. Okay. And then as I told you before, the complement of min term is the max term. That's why this becomes m sub 1, this becomes m sub 3, this becomes capital M sub 4, this becomes capital M sub 6, and then you have dot operators, and operators, right? Then you have this one, finally. Okay? And then you can easily say that this becomes this one, this becomes this one, this becomes this one, this becomes this one. Okay? After doing the complement, because you have complement operator here. So then you can see that in this case you are doing the AND gate AND gate operator multiplication with the max terms. That's why we have capital M here, and the indices are 1, 3, 4, 6. That's why you have 1, 3, 4, 6, and then you are doing the multiplication. That's why you have this product notation here, not the sigma notation. Okay. So here, if you want to calculate the Boolean function with Boolean variables, then you can use this truth table. Okay, you can see that you have three variables, x and y and g. Okay, that's why you have x and y and g, and x and y and g may have are able to get 0 or 1. That's why you have 2 to the 3 cases or combinations. That's why you have entirely 8 possible cases. That's why you have 8 possible cases. Okay, and then you have x, and then you are calculating capital E from here. So you have to put 0 here, put 0 here, put 0 here, and then you can get this result, and so forth. And then, as I told you before, in min term, you are getting the case where the result are number 1. That's why if you want to get the min term, then you can say that you have to see where the capital is 1. So this one, this one, this one, this one, this one. Okay, so this one is number 0, number 1, 2, 3, 4, 5. That's why you have 0, 1, 2, 4, 5. Okay, and then you are doing the summation. Then E is just like that, based on our calculation in our previous slide. Now we have to calculate the complement of the E. In this case, as I told you before, this is our E, and then the others are our complement. This one, this one, this one. These are our complement, E prime or E bar. That's why you can write down just like that. Okay, 3, 6, 7. Okay. So why we are doing the min term and max term? Every single component can be converted to min term at first, and then we are doing the addition or operator, and then we can get the final function. Okay, then we can simplify the logic structure. That's why here we can use we can define this equation with a logic circuit. So you have y prime at first, y prime, and then y bar, and then you have x prime, x bar, y, g prime, you have x and y, and then you are doing the addition. That's why you have AND gates, and then the result are combined with OR gate. That's why you have OR gate, and you can get the final function name. Okay, and then we can say that this is 2-level circuit because this is first level and this is second level. So 2-level means that the number of layers in terms of the gate. Okay, so this is first layer gate, this is second layer gate. That's why we can say that this is 2-layer circuit. So let's look at the other example. So in this case, you have A and B and you have multiplication. It means that you have AND gate. That's why you have A and B and you have AND gate. And then you have D plus E. So you have D and E and you have plus. Plus means or operator or union in set theory. That's why you have OR gate. And then you are having the AND gate with C. That's why you have another signal with C, and the result should be on another input of this AND gate. And then the result is combined with the plus notation, which means that we have a final OR gate here. Then the results are the inputs of this OR gate. And now you can see that this is first level, this is second level, this is third level. That's why we are saying that this is third level circuit or third level implementation. Okay, for the next, you have A and B and AND gate, C and D AND gate, and E and C and E last AND gate. And then you are combine all of these terms with OR gate. That's why finally you have OR gate. Okay, and then you can see that this is first level circuit. This is the second level circuit. Okay, that's why we can define that this is 2-level implementation. So now they are combined with AND gate, right? That's why we have final AND gate here. X is just a sole single input for this AND gate. So X is a single input for this AND gate. And then you have Y prime plus G. So Y prime, G, and you have plus. That's why you have OR operator. and then the result should be another input of this last AND gate. And then you have x, y, and g prime, x, y, and g bar, and then they are combined with plus notation. That's why we need OR operator. So this is OR operator. The result will be the last input of this final AND gate. Okay, that's why this is our circuit. Okay, so then we can see that it has two levels. Okay, so this is the standard form of circuit design or logic circuit design. So we studied about the min term and max term, and based on that, we can understand how you can organize the logic designs based on the definitions. So this is our end of the class today. So I'm saying a little bit faster than expected. And then in general, in my class, I'm using English and Korean for both. That's why combining with the Korean lectures, so we are covering all the detailed stuffs up to chapter 2.3. That's why for the next time, we're gonna study about two-level circuit design, and they are related to optimization. And then we will go further steps based on these textbook schedules. Thank you so much today, and I will gonna post another video fairly soon, maybe tomorrow or the day after tomorrow. Thank you so much.